Hey guys, hope you're well. Here we have a grade 10 June chemistry exam. It should take you 1 hour and it's 50 marks. If you want to download the paper, just check below the video in the description. Which of the following is a homogeneous mixture? Okay, so let's quickly talk about what a mixture is, because some of these, we need to make sure that these are all mixtures. So, a mixture, let's talk about that. We've learned that in chemistry, we've got mixtures, and then you get something called pure substances, right? We've spoken about that. Now, pure substances are things like elements or compounds. So, for example, if you have a container, and in that container you only have let's say you've only got nitrogen, then this would be called a pure substance, because there's only one type of thing, right? If we had let's say, for example, a container filled with H2O, so let's say H2O, so H, O, and H, and then there's another H. Okay, let's do this a little bit bigger. So let me just quickly say, this is a pure substance because it's just elements. Okay, if we have like we were going to say H2O, let's draw it out a bit bigger. So H2O, which is actually just water. You know, you drink H2O, H and O, but these are bonded together. It's all bonded together. So can you see that you have so this is called a compound because it's two or more different elements bonded together, and then here you've got another compound. Can you see you only have one kind of compound in this container? So you only have one kind of thing. So this is also a pure substance because there's only one type of thing. There's a water and another water. Okay, but now if I have a container that is filled with, for example, a nitrogen element or atom like that, and then I have a water compound, then this is no longer a pure substance, because now you have two or more different things. So this would actually be called a mixture. A mixture is when you have, and we have spoken about this is just a quick summary. A mixture is when you have two or more different things. Okay, so now, let's have a look here which of these are mixtures. So if you have sand and water, that is definitely a mixture. If you have muesli, now remember muesli, the stuff you eat, we can definitely see there's different things here. There's the oats part, there's a raisin, there's like a dried banana, and other things. So there is definitely a mixture. If you have a salt solution, what that means is when you put salt with water. So that is definitely a mixture. However, if you have carbon dioxide, so carbon dioxide has a carbon in the middle and then an oxygen and an oxygen. So that is what CO2 looks like. So if you have a container filled with CO2, then let's see what that would look like. So these are all bonded together. CO2. And then you would have another little CO2 floating around, CO2. So if we had a whole bunch of CO2s in this molecule, can you see that you're in this container, can you see that we only have one kind of thing in this container? Some of you are like, Kevin, what do you mean we only have one kind of thing? There's oxygen and carbon. Yes, but those are bonded together. It's not like we have carbon over here and oxygen over here. This is bonded together. That is a compound. So here we have one compound and here we have the same compound. So in this container, we only have those compounds. So carbon dioxide is not actually a mixture. This is a pure substance. So we are not going to look at this one for this question because they want to know which of these is a homogeneous mixture. So now what we need to talk about is the different types of mixtures. You get homogeneous and you get heterogeneous. So let's quickly talk about that. So the way that it works is that, okay, so these are all mixtures. By the way, this is milk. Is milk a mixture? You might say, Kevin, there's only one type of thing, but that's not correct. Inside milk, there is water, and there is cream, and there's a whole bunch of other stuff inside milk. So milk is a mixture. Milk is a mixture. It's not just one kind of thing. There's different things in there, okay? So, and this is also a mixture because there is sand and water. And then muesli is also a mixture because it's got raisins, oats. So there's different things, okay? So all of these pictures on the screen right now are mixtures, okay? Now, we need to talk about there's two different types of mixtures. Within mixtures, you get homogeneous and heterogeneous. Okay, so if I look over here, does everything just look like one kind of thing, or can I see different parts? Well, I can definitely see different parts. I can see there's sand and there is the water part. Okay, so when I can see different parts, that is called heterogeneous. Now, if I look at muesli, I can see there's the oats part, there's a raisin, and, for example, a dried banana, and a whole bunch of other stuff. But the point is that I can see different parts. So because I can see different parts, that is heterogeneous. Now, when I look at milk, I know if I look on the back of a milk box that inside milk, on the ingredients, it doesn't just say milk. It says there's water, there's cream, there could even be sugar. So there's a whole bunch of stuff inside here, right? So it is a mixture. It's not a compound. It is a mixture. But it looks like only one thing. I can't see the water, I can't see the cream, I can't see the sugar. All I'm seeing is milk. It just looks like one thing. So when it only looks like one thing, then we will say homogeneous. It is homogeneous, okay? So this question says, which of the following is homogeneous? Well, we know that sand and water, we said, is heterogeneous. Muesli is heterogeneous. Now, I don't have a salt solution on the screen, but if you had to go into your kitchen right now and take water and take a little bit of salt, throw the salt into the water and shake it up, what you would notice is that it's just going to look like one thing. It's going to be very difficult to be like, oh, there's the water and there's the salt. No, it's all going to be one thing, and so that is going to be homogeneous. So salt is a homogeneous mixture. If any of you said the answer was carbon dioxide, be careful. It does look like it's homogeneous, but the problem is it's not even a mixture. There isn't more than one thing. It is only one thing. And so it's actually just a pure substance. So a homogeneous mixture is a mixture. So that means there are more than one thing in the container, but it looks like there's only one thing because of the way that it's been mixed. Then it becomes a homogeneous mixture. The process whereby a substance changes from a liquid to a solid. Okay, so let's think about that. Very easy question, because if you have a liquid, okay, so let's say you've got some, let's go get a glass of water, and then we've got some ice, because they said it goes from a liquid to a solid, okay? So what is that called when you put water in the freezer and it turns into a solid? Well, that is called freezing. You put it in the freezer and it turns into ice. What is the correct formula for lead with a 2 and nitrate? So we need to remember a couple of things. One of them is that when they put a Roman numeral over there, that is when we have a transition metal, which, remember, are these ones inside this block over here. Okay, so those are transition metals. Lead is Pb. So where is Pb? Pb. And so what they're trying to tell us is that lead, which is Pb, can have, remember, when it's a transition metal, it can have different charges. It can have +1, it could be +2, it could be +3. They can go up to +4, +5, +6, +7. But they're telling us that there's a 2. So it means that it's a +2. It's always a plus for those ones, for the transition metals. Now, nitrate is NO3. You can see all of these have NO3 in them, right? But, and here we have it here, NO3. But we need to know, and it's called nitrate, we need to know what its charge is. Now, its charge is -1. Can you see there? There isn't a -2 or a -3. It's a -1. You need to know these, okay? So we're going to put -1. Now it's easy. We've been at this situation before where you've got these two things next to each other. So all that you're going to do is the 2 is going to go over there, and the 1 is going to go there. So it's going to be PB. I'm going to put the 1 there for now, but we will take that away. And then the NO3, that entire thing must get a 2. You must put the entire thing with the 2, okay? And so when there's a 1, you take that away, and then you can just move it a little bit closer. And so there we have PbNO3 with a 2. So it's going to be this one over here. The electronegativity of sulfur. Okay, so that is something on our periodic table. So let me quickly grab that. So sulfur is S. Okay, so there's S. Now, if you're in a test and you just cannot remember what electronegativity is, it happens if you're feeling stressed sometimes. Well, then just look at this key over here. This is a key directly from the exam paper, this whole periodic table. So electronegativity is this number over here. So there it is, 2.5, 2.5. Two substances that can be classified as molecular substances are... Okay, so we need to remember the different types of bonding that we get. We've looked at ionic bonding, which is where you have a metal plus a non-metal. Then we've looked at covalent bonding, and that is when you have a non-metal plus another non-metal, or you could have multiple non-metals. Then we get metallic, which is where you have a metal plus another metal. Now, each of these different things, so ionic number 1, covalent number 2, and metallic number 3, they bond, they have different structures when they bond. With ionic, you would have, for example, sodium chloride. You would have a sodium and then a chloride. Then a sodium, chloride. Sodium, chloride. So what it does is it forms a lattice. We call it an ionic crystal lattice. Then I'm going to quickly skip covalent and I'm just going to come to metallic. So with metallic, it's normally just one type of metal. So let's say, for example, we have magnesium. It's a metal. Okay, so what would happen is that you would have a whole bunch of magnesiums. I'm not getting too technical with these. I just want to quickly put their charges. And then with magnesium, it has a valency of +2. And then we've got all these electrons just randomly scattered all over the place. That's how metals. We call it a sea of delocalized electrons. Okay, that's what metallic looks like. Now, with covalent, there are two different types. There's two different ways that covalent substances exist. 99% of all covalent substances exist as simple molecular substances. And that's what this question is talking about. Molecular substances. And that just looks like this. Let's say we've got a covalent substance. Now, a covalent substance is two non-metals. So, for example, hydrogen and oxygen, which is water. So if you had a container filled with water, you would just have a whole bunch of water molecules floating around. So this water molecule and this water molecule, they're not physically bonded together, okay? They're just floating around. They're not connected in any way. They're not connected like you would see over here. They are just floating around, because here, remember, there is like an ionic bond in between all of these. And over here, we have got metallic bonds between all of these. Okay, there are metallic bonds. But over here, there's no physical bond in between. Each one exists by itself. Okay, so that is what a simple molecular substance is. Then we get the other 1% of covalent is what we call giant network or giant covalent network structures. And that would be things like graphite, diamond, silicon dioxide. These are some common examples that we use in high school. Okay, so they are looking for two substances that can be classified as molecular. So that means they are looking for this category over here. So definitely it has to be two nonmetals, because if it's got a metal, then it's either ionic or metallic. So we need our periodic table quickly. So if we look at ammonia, now this is where it becomes important that you know what ammonia is. Ammonia is NH3, and then hydrogen chloride is H with a Cl. So if you look at nitrogen and hydrogen, both of those are nonmetals. We know that hydrogen is a nonmetal, and then everything on the right-hand side of the step is a nonmetal. So these are all nonmetals. So nitrogen is over there. So this is definitely covalent. And this one at the top is definitely covalent. So this one could definitely be the answer. Let's quickly go down to B. This one has magnesium in it. Now magnesium is a metal. So this definitely cannot be the answer, because as soon as it's got a metal, then it's either ionic or metallic. It doesn't matter which one it is, because we know that for it to be covalent, we need two nonmetals. Okay, so it can't be that one. This one also has magnesium. You see how it's got magnesium over there, so it can't be that one. And then it can't be this one, because this one has graphite, and graphite is one of the giant covalent network structures. So the answer would have to be A. Ammonia is NH3, like we said, so it's two nonmetals. And then hydrogen chloride is also that's HCl, so that's also two nonmetals, so that's covalent. And ammonia and hydrogen chloride are not part of these 1% over here, so they are in this category over here. So that means that the answer for this question would have to be A. This question starts off by saying, differentiate between a thermal conductor and an electrical conductor. Okay, so the word thermal, I want you to think of heat, and the word electrical, think of electricity. The word conductor means that it allows something to move through, or it can move something. So a thermal conductor is good at conducting heat, and then an electrical conductor is good at conducting electricity. Okay, now from the list above, so we've got glass, copper, it says here, study the 7 substances below. Okay, so we've got glass, copper, sugar water, nickel, carbonated water, air, and carbon dioxide. Right. From the list above, identify a thermal conductor. Now, what we need to understand is that we've got three different types of material. We've got ionic substances, metallic, and covalent. Now, metals are very good at being thermal and electrical conductors. We've looked at this before. Metals are really good at that. Okay, so from the list above, identify a thermal conductor. So it'll definitely be the one that is a metal. Now, glass is not a metal. Glass is a covalent substance. How do we know that? Well, remember when we looked at the differences between metals and non-metals? And what we said was there was this thing called, you could think of malleable. Remember we looked at that lesson where we said that metals are malleable, meaning that you can bend metals. Whereas if you looked at a non-metal, so let's just say that this was metals, and then we said that non-metals are brittle. For example, if you take a piece of glass and you try to, let's say you're holding a piece of glass, right? Or let's say you take a hammer and you hit the glass is going to shatter, right? It's not going to bend. Glass does not bend. So we said that thermal conductors are metals. Metals are good at being thermal. So thermal conductors. So glass is a non-metal because glass is brittle. So it can't be glass. Copper is a metal. So I'm going to go with that one. Copper is a metal. Now, which of these materials is magnetic? Oh, sorry, just coming back to 2.2.1, I see there's another metal over here, which is nickel. So you could say both of those. You could say one or the other. So there are three main elements that we consider to be magnetic. We call them ferromagnetic materials. They are nickel, cobalt, and iron. Their symbols are Ni, Co, and iron is Fe. So what is a magnetic material? You could say nickel. A heterogeneous mixture. Okay, so we've spoken about homogeneous and heterogeneous. So heterogeneous is when it's like a chicken salad. Maybe you've seen my example of chicken salad. If you look at a chicken salad, does it just look like one thing, or can you see different parts? Well, no, you can see different parts. You can see chicken, you can see the lettuce, you can see tomatoes. So because you can see different parts, that is heterogeneous. Now, this one's actually quite tricky because, okay, if you had to take sugar and water, so you could go try this now. Take a glass of water, take 1 teaspoon of sugar, throw it in, mix it up, and it's just going to look like one solution, okay? So you're not going to see the sugar and you're not going to see water. It's just going to look like one solution. So because it's not going to be different things, that's going to be homogeneous, not heterogeneous, homogeneous, okay? Now, carbonated water now, if you go look on the internet, some people will say this is heterogeneous and some would say it's homogeneous. Let me explain. If you go buy soda water from a shop and the bottle has not been opened, it will look like plain water. So that would be homogeneous. However, and this is where the question gets this a little bit wrong because it could be both heterogeneous or homogeneous. But what they mean was when you open the soda water, so when you unscrew the lid, all of a sudden the bubbles start rising to the surface. In that moment, can we agree that you would see water and you would see bubbles? And that is what the question was talking about, when you can see the water and the bubbles. So because you can see two different things, that would be heterogeneous. So this would be carbonated water. If that one confused you, I don't blame you. It's not a good question. Okay. Now, an electrical insulator. What is the opposite of a conductor? It's an insulator. So if a conductor is good at conducting or moving heat and electricity through, then an insulator is bad. Now, if we know that conductors are typically metals, then insulators would be non-metals. So we said that glass is a non-metal. Remember, it's brittle, meaning that it doesn't bend. So that means it's a non-metal. That was one of the properties of non-metals, is that they cannot bend. They are brittle. And so I'm going to use glass over here. But technically, air is also a non-metal. Air is just nitrogen and oxygen and some other gases, but they're all non-metals. There's no metals in air. That would be crazy if in the air right now there was like copper hitting you in the face. It's like, bro, don't walk too fast, you're going to hit your head. So air, you could also say that one. And carbon dioxide. Carbon dioxide is not a mixture, but I mean it's a bond between carbon and oxygen, which are non-metals. So carbon dioxide is also an option. You only have to choose one of those for that question. So here are all the questions that we will be looking at, but I will be splitting them up onto individual pages just to give ourselves a bit more space. So let's see what this one's all about. It says that the grade 10 learners were investigating the effect of heat on ice. The temperature was recorded every 5 minutes. The following results were obtained. Okay, so they're going to take some ice. You can see the temperature starts at -10 at the very beginning because that's at 0 minutes. And then all that they're going to do is just increase the temperature. So, or sorry, no, that's not what they're doing. They're adding heat. So maybe there's like a flame or something. And then they're monitoring the temperature of the water or the ice. So it starts at -10. Then for all of that time over there, for 5, 10, and 15 minutes, the ice is at 0 degrees. We'll talk about why that's happening. Maybe some of you know that already. And then the temperature goes to 25, 45, 75, and then it stops at 85 again. Okay, so this is, if you want to understand what this is all about, this is about your heating curve, right? You take something. I've showed you a heating curve before, where this over here was time and this over here was temperature. So we start at what do they start at? -10. So we can start here at -10, and then if you heat it up. If you add heat, then what would happen to the temperature of the water or the ice? It would begin to increase. It increases, and then when you get to 0 degrees, I've showed you guys this before. We noticed that it became flat, and that's what we're seeing over there. Okay, so all of that's happening, and then after it has, because over here it's a solid. Over here it's busy going from solid to liquid. So here it's busy melting, and then once it's all melted, then the temperature begins to increase again, as we can see over here. And then usually if it was water, usually at about 100 degrees, it would become flat again. But for some reason, we're hitting 85. So let's see if they ask us about that, because that's quite interesting. Okay, but this is all about heating. So the first question says, define the term boiling point. Now, of course, we know what boiling is, right? If you want to make some food, let's say you want to boil the kettle, right? What's in the kettle in the beginning? Liquid, like liquid water. Then you put the kettle on and the water begins to boil, and you can see if you look out on the outside of the kettle, there is steam coming out. So boiling is when you're going, we know that boiling is when you go from a liquid to a gas. However, that is not what you must say when they ask you for the definition. The definition is actually quite weird, but let me try explain to you how this definition works. So let's say we have a pot, okay? And in that pot, we have water. Right. Now, and here's our pot. Here's the stove top. Okay, that's the stove top. And this is where we are applying heat. You know, when you have a gas stove or you have an electric stove, you put the temperature on, and what will happen is that this water is originally, maybe it's at 20 degrees Celsius. Maybe that's the temperature in your house, or that's the temperature that the water comes out of the tap. So in there, you've got water molecules that are busy moving around. Okay? Now, as you switch the heat on, some of these water molecules, before they even begin to boil, some of them are going to already start going into the gas phase. We call that evaporation. Look at your swimming pool if you have a swimming pool. You would notice that in summer, if you don't have a cover over your swimming pool, the level would eventually drop over a couple of days. Why? There's no boiling happening. Boiling only happens for water at about 100 degrees. But what's happening is that there is the process of evaporation, which is also when you're going from a liquid to a gas, but it's different to boiling, okay? At evaporation only takes place on the surface. So these molecules up here on the surface, if they can get enough energy, they can quickly be like, I don't want to be a liquid anymore, I want to be a gas. And then they jump up and then they get into the gas phase. So what happens is that you're getting this gas developing over here. Okay? Now, eventually, if more and more gas molecules keep collecting over here, eventually the gas molecules over here will have the same pressure as the air molecules in the atmosphere that was already in the air before we started this process. You know, in your house you've got air. Well, I hope you do. If you don't, you'd be dead. But you've got air in your house, right? And that air consists of air molecules like nitrogen, oxygen, and those air molecules have a certain pressure. In the beginning, there is no vapor pressure over here. There's no vapor pressure. But as we begin the boiling process or the evaporation process, and then eventually the boiling process begins once the water reaches 100 degrees, then there is going to be a lot of water vapor molecules in the gas phase. Okay, so here they are in the liquid phase. Here they are in the gas phase. Now, boiling is what happens when this pressure over here is equal to this pressure over here. So the definition of boiling is the temperature. It is the temperature at which the vapor pressure, which is this one over here, of the substance, which in our scenario is water, equals the atmospheric pressure, which is this stuff over here, the pressure that was already in the atmosphere. That is what boiling is. Now it says, name the instrument used to measure temperature. Well, we know that a thermometer is what you use to measure temperature. Thermometer. The next question says, identify the independent. Now your independent variable is usually always the one that's at the top over here. If they gave it to you as a graph, it's usually the one that's at the bottom over here. Okay, so in this case, it's just going to be time. Now, this question says, on the graph sheet provided, now this is the ugly graph sheet that they provided. Have you ever used one of those like brown books? I don't know. My parents used to buy me these ones and I hated them. Like if you write too hard, your pen literally just tears through the paper. On the graph sheet provided, draw the graph that represents the data in the table below. Okay, so what you would have is you would have you'd need a y-axis. You would need an x-axis. Okay, obviously you would use a ruler and all of that. Then you would label, so just literally label it like that. That's your y-axis, that's your x-axis. So that already gets you like 2 marks. So time, in brackets, minutes, and then temperature in degrees Celsius. Then remember to put a heading. Sometimes you get a mark for that, sometimes you don't. So what we can do is just say something like graph of temperature versus time. So this one's always your y-axis, this one's always your x-axis. Okay, now let's go plot the values. So the temperature starts at -10. So let's actually just extend this down here to -10. Then this is 0 degrees. And then it goes all the way up to 85. So I'm going to go up in tens. So 10, 20, 30, 40. Obviously you would have this on a ruler. It would look a lot better than mine. 70, 80, and then let's just go 85. Now you're just going to go plot the points. So this first point is at 0 and -10, which would be over there. Then 5, oh, I need minutes on my x-axis. Okay, so it goes from 5 up to 40. So 5, 10, 15. Obviously this would be equally spaced when you are doing it with a ruler. 30, 35, 40. Okay, so then 5 and 0. So 5 minutes, 0, 10, 15, 0. Then 20 and 25. So 20 and 25 would be there, because that's 25, right? Then 25 and 45. So 25 and then 45. And then 30 and 75. And then 35 and 85. 35 and 85. And then, like, you would never do it above that, but I'm just quickly doing it freehand so you can just see how it all works. And then you're just going to go connect that. So there, obviously using a ruler. This would actually be perfectly as a straight line. and then it goes straight again. Okay, so you get the idea of what your graph would look like. Now, name the process that water undergoes at the time between 35 and 40. So let's go back to our graph. Between 35 and 40, we can see that the graph is flat. Why it's not happening at 100 degrees Celsius, I'm not 100% sure, but that can sometimes happen if the water maybe has salt in it, or maybe we are not at sea level. Maybe we are very high up in the mountains where, temperature, water only boils at 100 degrees under special or under normal conditions. But if we are not at normal conditions, as I said, maybe there's salt in the water, maybe we're on top of a very high mountain where the pressures are different, so then the water would boil at a different temperature. I don't know. But what we know is that over here, we were ice. Over here, we were melting. Over here, the melting has finished. So then that means over here, we are liquid. Sorry, instead of saying ice, we could say solid. So here we are liquid. Here we are busy going, we're in the liquid phase. Now what comes after the liquid phase? Well, now we are eventually going to start going from a liquid to a gas, which is boiling. That's a boiling phase. So it says, name the process that water undergoes at the time over there. So we can just say boiling. Well, remember, I have showed you exactly how a cooling curve works and a heating curve. Remember how I showed you in that lesson on a heating curve that it typically went like this, right? And I spent quite a bit of time explaining why do the lines become horizontal over there. Now, specifically, we are looking at this one over here. Okay, but it actually works for this part over here. So I would definitely recommend you go and check that video just to go look for it. It's the heating curve where I explain it in a lesson, okay? But I'm going to try to just summarize it now as well. So what happens is that this is temperature. And you can think of that as, remember, we know what temperature is. It's kinetic energy. It's how fast are the molecules moving. And this is time. So in this section over here, what's happening is that these molecules are all in the liquid phase. And as we are adding, and then remember, we've got like some type of flame. Maybe there's a flame, some type of heat. And as we keep adding heat to the liquid, what is going to happen to the molecules inside this liquid as you are adding heat? They're not boiling just yet. We're not here. We're over here. So what happens is that as you are adding heat, these molecules are beginning to move faster and faster and faster. So that means their kinetic energy is going up, meaning their temperature is going up. And that is why we can see there is an increase over here. That makes sense. But eventually, these molecules are moving so fast that eventually they're looking at each other and they're like, yo, I think we are at the time, or we have the right amount of energy where we can now start to become gas molecules. So what then happens is this heat over here continues to be applied. And what happens is that all the extra energy that is coming in from this heat, they're not using these molecules are no longer going to use that heat to become faster. Instead, they are going to use that heat to jump into the gas phase. They're going to jump into the gas phase. So are they going to be moving faster? No, because we just said that they are not going to use that energy to go faster anymore like they did over here. Instead, they are going to use that energy that is being applied to jump into the gas phase. So while all of them are busy jumping into the gas phase, they are not going to start moving faster. So we are not going to see this line going up and up and up, because that would mean that they are going faster. Instead, they are going to remain as fast as they are, but and that's why we can see this becoming horizontal over here. They're not going faster and faster, and they're rather using the energy from the heat to jump. Does that make sense? So that's why we're seeing it horizontal over here. Okay, but now we're not going to say jump when we're giving our answer over here. It's not actually the jumping where they're using the energy. What they are really doing is the following. These two molecules, or actually all of these molecules, they are slightly attracted to one another because of intermolecular forces, which you'll learn about a lot in grade 11. There are little intermolecular forces that are attracting them towards each other. Think of it like a magnet. And so what they do is they use that energy to overcome, or to, you can say, to overcome, or some in the CAPS curriculum, you can say break. If you're in the IEB curriculum, they don't like you to use the word break, but you can break away, or you can break these little intermolecular bonds over here. And then if they can break those, then they can jump into the gas phase. So that is why we see a horizontal line over here, because they are using the energy from the heat source to break those little bonds and then go into the gas phase. Okay? They're not going to use the energy to become faster and faster and faster. That is what would only happen over here and over here. Okay, so how do we answer this? So it says, name the process that the water undergoes. So we said that was boiling. Now, how did we know that was boiling? Well, what we can see was that the temperature remains constant. This indicates that kinetic energy is constant. During the boiling process, the external heat is used to overcome. If you're in the CAPS curriculum, you can say break. Most of you are CAPS, by the way. Overcome or break the intermolecular forces between the molecules. Okay, and that's pretty much all that you need to say over there. The diagram below shows the element hydrogen, which has 3 isotopes. Do you remember what isotopes are? If not, go check it out. I do talk about isotopes in some of the videos. But pretty much what we've learned is that, let me get a periodic table quickly, is that atoms have, atoms contain electrons, neutrons, protons. And by looking at this number and this number, we can get a perfect idea of how many of each one it has. What I've told you guys in previous videos is that these numbers here tells you the number of protons. Okay, that's the number of protons. Now, if it is a neutral atom, meaning it's not positive or negative, it's just neutral, then that is also the number of, so if neutral, then that is also the number of electrons, let's say here, then also the number of electrons. Most times it is going to be like that. It's going to be a neutral atom where it's not going to have a charge, positive or negative. Okay? Then by looking at this number at the bottom, that is the mass of the molecule. So that's your mass. So we know that mass of a atom is the number of neutrons plus protons. Why not electrons? Well, we've learned that electrons do not have any mass. I mean, they do, but it is so tiny that we assume they don't have any mass. Okay? So, if I know, for example, that this one over here has 11 protons, then if I say 23 minus 11, that'll give me 12, and that'll have to be the neutrons. So it's got 11 protons and 12 neutrons so that the total mass is 23, right? That's what we've learned up till now. Okay, so now with that, we can go and begin this question and start talking about isotopes. Because the very first question asks us to define the term isotopes. Let's quickly talk about isotopes. I could give you Na 23 11, and I could give you Na 24 11. So what is the difference between these two? Yes, we can see the mass is different, but what does that mean? Well, if we look at the number of protons, electrons, and neutrons, let's see what the real difference is. Let's go there and there. Okay, so, whoops, let's do that. So, if we look at the protons, they both have 11, 11, and 11. If we look at the electrons, that'll also be 11 and 11, assuming that this is a neutral atom without any positive or negative charge. Then the amount of neutrons for this one would have to be 12, but in this one it would be 13, because 13 plus 11 gives us 24, which is what they said. And then this one is 12 plus 11, which gives us 23, which is what they have. So this, or these two things, are isotopes. So therefore, isotopes are the same element. It's the same element, sodium and sodium, but with different numbers of neutrons. So if we had to go and give a definition, we would say that it is atoms of the same element with the same proton number, but different amount of neutrons. So the protons have to be the same. Sometimes in a test they'll do something like this. They'll go x11, x12, 22, 22, or 23, 23. And x is just a random thing. And they'll say, are these protons? And a lot of learners will say yes. But if this is 11 and that's 12, that means the protons are not the same. But isotopes have to have the same proton number. Okay, so don't let that confuse you. All right, so that's the first question. Now this one says, the table below shows 3 isotopes, the number of particles, which is incomplete, and the relative abundance of each isotope. This question says, complete the table by writing only 4.2.1 and the correct number of particles. Okay, so 4.2.1. Okay, so let's have a look. If we look at this first one, number of protons, well, let's first look at this. Number of so we're looking at protium first. Okay, protium first, because here we have protium, deuterium, tritium. So how many electrons does it have? Well, we can see it's got 1 electron, 1 proton. So we can just say here, 1. Then how many neutrons does it have? Well, if you look here, it's got 0. You can see it's got no neutrons. So you could just say, you could even work it out if they didn't even give you these pictures, because the total mass is 1 and it already has 1 proton, so it can't have any neutrons. Then this question, deuterium. So what is its mass number? Well, the mass number is the protons plus the neutrons. So that's 1 plus 1, which is 2. And then this one says, what is the number of protons of this one? Well, it would also have to be 1. We can even see it says here 1, but if these are 1, then this one also has to be 1, because isotopes have the same proton number. So there we go. 1, 0, 2, and 1. Now this one for 3 marks. Use the table above and calculate the relative atomic mass of hydrogen. Okay, so I have showed you guys how this works before. Remember, I've showed you how to calculate when they give you the percentages and all of that. If not, you need to go check that video out. So pretty much what we do is you just take the percentage of this one, so 99.985, multiplied by its mass, plus this one's percentage, 0.015, multiplied by its mass, which was 2, plus, and then this one is just 0 because they said that it's negligible. Okay, and then you divide all of that by 100. As I said, I have showed this before in a previous video on how to calculate relative abundances and all of that. Now, if we go calculate this, you end up with an answer of 1.00015, and then mass is always measured in grams in chemistry. Okay, so go check out that video if you haven't watched it, where I do explain this. Electrolysis is the process of using electricity to decompose water into oxygen and hydrogen. Okay, so maybe you haven't even learnt about this before. Most times they don't even show this in grade 10. That's fine. I don't think that you are supposed to know it, but let's just see the types of questions that they're going to ask. Okay, so they said that they're going to decompose water into oxygen and hydrogen. So you're taking water and you're breaking it down into hydrogen and oxygen. Okay, so the first question says, identify the bond in water. Choose from covalent, ionic, metallic. Okay, so we've looked at the different types of bonds, and in summary, we know that ionic is when you have metal plus non-metal. Covalent is when you have non-metal plus non-metal. And then metallic is when you have metal plus metal, as the name suggests. Metallic. Get it? Okay, so when you have water has hydrogen, which is a non-metal, and it's got oxygen, which is a non-metal. So water is a non-metal and a non-metal combined. So that would have to be covalent. So we'll say here, covalent, non-metal plus non-metal. Or let's rather say non-metal bonded to a non-metal. Draw the Aufbau. What is an Aufbau diagram? The Aufbau diagram is that box diagram. Remember where it goes like this, like this. So if you haven't checked that out, well, you need to make sure that you know Aufbau diagrams. But of course, I will explain the basics now as we go through this question. So they want us to do the Aufbau diagram of oxygen. Okay, so I know that I've blocked the other questions, but that's fine. I'll show it now when we get to that one. So they want us to do the Aufbau of oxygen, which is over here. Now remember, the basics of the periodic table is that this is row 1, this is row 2, and this is row 3. And of course it can go further, but we don't need to get that far for this question. The next thing to remember is that this part, all of this on the left, is what we refer to as the S block. And then on the right hand side is where we call it the P block. Okay, so the way that it works now is I like to do the electron configuration first. Remember that whole 1s2, 2s2, 2p6? Let's quickly go over that a bit. So we need to get all the way to oxygen over here, which has 8 electrons, but we have to start over here. So we're starting in row number 1. Okay, you see how we're in row number, see how we're going in row number 1. So we start here, which is row number 1. Now, we enter the S block first because we're starting over here and we're going to drive our car. So we're going to drive our car from here. So we enter the S block now. And how many electrons are there? Well, this is 1 electron. Oh, remember, sorry, that this helium here is part of the S block. My bad, I forgot to mention that. This is part of the S block. Okay, so we've crossed off that one. And now we've crossed off that one. So how many did we cross off there? We've crossed off 2. Now we're going to go down. So we're driving our car. Now we're going to start over here. And we're going to drive all the way like that. So we're entering now into row number 2. And we're starting off by entering the S block. And we cross off lithium and we cross off, don't know what happened there. We cross off beryllium. So how many things did we cross off in the S block? We crossed off 2. Now we are over here. So this is now also in row number 2. But now we are entering the P block. And now we're going to cross off 1, 2, 3, and then 4 gets us to oxygen. So we do it like that. So that is the electron configuration of oxygen, okay? Now to do it in an Aufbau diagram, you're going to put 1s, 2s, and 2p. So you're going to put 1s, 2s, and then for p, you put 3 blocks, remember? And then you put, going up, you say energy. Okay, and now you just fill everything in. So you can see if you add up, we know that we need to get all the way to 8. So you put, starting at the bottom, you put 2 there, like that. Now, when you get here, you're going to put 1 in each one. 1, 1, 1. So how many electrons have we used? Well, there's 2 over there, 2 over there, so that's 4, 5, 6, 7. Then you put number 8, like that. That's the correct way. The wrong way would have been to do it like this. You would have gone there, 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 and then you would have gone up, down. Okay, no, that's not big enough, Kev. You would have gone up and down, and then up and down, because that also makes 8. But then this one is empty. So the rule is that you must first do it individually, and then come back and start over. Okay, and so this is what the Aufbau diagram of oxygen would look like. Okay, this question says, write the SP. Now this is called SP notation. See, there's a S and a P. Some of them also have a D as well, but you get the idea of an oxide, which means oxygen, but then they use the word ion. Very important. Okay, guys, so remember we have spoken about electron configurations. Now, when they talk about an ion, let's quickly talk about that. So it's definitely oxygen, okay? So we know oxygen, right? Now, we've just looked at oxygen on the periodic table. We know that it has 8 electrons in total. So, and that's what we saw over here. But now we've also learned that you also, sometimes they don't give you the proper oxygen or nitrogen. Sometimes they give you the ion, okay? Now, let me try explain what an ion is. So, we know that a normal oxygen, it's got 8 protons, okay? So, 8 protons. Now, if it is a normal, well, actually, let me use fluorine as an example, because there's something here that's going to just, because this is 8 and this is double, some learners get confused. So I like to use this one over here. If we look at fluorine, now, fluorine has 9 protons, and if it's a normal fluorine, then it has to have the same amount of electrons. Same amount of positives, same amount of negatives. If it is a neutral atom, then to work out the number of neutrons, we look at this number here. So it has a total mass of 19, and then you minus the number of protons, so it would have to be 10 neutrons, right? Because remember that the mass, which is this number down here, is always the neutron number plus the proton number. And if the proton number is 9, then the neutron number would have to be 10, because 10 plus 9 is 19. That is what life would be like if it was a normal fluorine. But what about an ion? Well, let me talk to you about what an ion is. An ion is when an atom has a charge. How can an atom have a charge? Well, if you look at this one, it's got 9 positives and 9 negatives. So what would the overall be? Would it be positive, negative, or would it be neutral? Well done if you said it would be neutral, because it's got 9 positives and 9 negatives. But what if we had a fluorine ion, which, let's say it has 9 protons, but let's say it has 10 electrons. And then the neutrons won't change for that kind of example. So now it's got 9 positives but 10 negatives. So if you have 9 positives and 10 negatives, what would your overall charge be? Well, now all of a sudden, it would be -1, right? Because 9 positives and 10 negatives, it would be -1. As soon as it has a charge, then we call it an ion. What if we had a fluorine which has 9 protons and 8 electrons and 10 neutrons? Well, then you've got 9 positives and you've got 8 negatives because electrons are negative. So what would your overall charge be if you have 9 pluses and 8 negatives? Or 9 minus 8 is 1. So now you would have a positive charge. So when you have a negative charge, that's called an anion. And when you have a positive charge, that is called a cation. So an ion is an atom that has an unequal number of protons and electrons. Okay? So the problem is, though, is that they asked us to do an oxide ion. So it's an oxygen ion. Okay, so here's oxygen. But now how are we supposed to know if this ion is going to have more electrons, less electrons? How do we know? Well, it's actually very easy. All you do is you look at the valency number. Can you remember what that is? We have spoken about that in the past. So valency number is when you have +1, +2, +3, +-4, -3, -2, -1. Don't confuse that with valence electrons. Remember we had a lesson where we spoke about valency and valence electrons. There was a difference, right? So we know then that oxygen is -2. Now think about that carefully. We already know that it has 8 protons. Normally, it would have 8 electrons. But because it's the ion, it's going to have a charge that is negative. So how do you become negative? Should it gain more electrons or less? Well done if you said it should have 10 electrons. Because what is 8 positives take away 10 negatives? Well, that would give you -2. And that's exactly what it is. If it was one of these ones, then it would have less electrons so that it can become positive. Okay? So we now know that an oxygen ion, or oxide is what they sometimes call it, is a normal oxygen with 2 extra electrons. So then all we need to do now is, how many electrons does it now have? 10. So then all that we do is we just need to do the sp notation until we get to 10. So this is 2 electrons plus 2 electrons plus 4 electrons, which gives us 8, which is what we had. But now we want to do it so that we get all the way up to 10. Okay? So all that we do is we can now do the sp notation 10 blocks. So instead of 8 blocks, we're going to do 10. So it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you ready? Let's begin. So remember, we always start in row number 1. So I'm going to say 1. Then we enter the S block. So we enter the S block and we block off 1, 2. Okay? Then we enter row number 2 and we enter the S block, 1 and 2. So we're going to block off 2 over there. Then we're still in row number 2 over here. But now we are in the P block. Remember, this is the P block. And we block off 1, 2, 3, 4, 5, 6. And that will give us 10. Because 2 plus 2 is 4 plus 6 is 10. So that is what your electron configuration will look like. Or your sp notation of an oxide ion. And now the last question says, draw the Lewis diagram for an oxygen molecule. Okay, so we've looked at Lewis diagrams before, but now they want us to do an oxygen molecule. So that, okay? So what we know is that oxygen, well, there's one oxygen and there's another oxygen. So let's quickly grab our periodic table. And we know that with Lewis diagrams, we count the group. So this is group 1, 2, 3, 4, 5, 6, 7, and 8. So oxygen is in group 6. So it's got 6 electrons. So we always start 1, 2, 3, 4. Once you've done those 4, then you can go 5, 6. Okay, now the same is true for this one. 1, 2, 3, well, we're supposed to do it the proper way. 1, 2, 3, 4, 5, 6. Now all that you do is you just put these two things next to each other. Let's actually do this let's use crosses. Wait, let me start again, sorry. 4, 5, 6. So all that you're going to do now is like almost play like a game of Tetris, where you're just going to combine those two, and you're going to combine those two. So what you're going to get is 2 oxygens next to each other, and then you could put that, and then let's just quickly do this one. And then we said that this dot is going to link with that cross, and this dot is going to link with that cross. So what you get in the middle here is that, and then you can just put these two in the middle as well. So you get something like that. And so there is your Lewis diagram. The following graph shows the first ionization energy for a few elements. Now, it's important that you understand what ionization energy is. Of course, we have made videos on that. And if you haven't watched those videos on ionization energy, then of course you should do that before trying to do this question. Pretty much what ionization energy is if we look at let's say we've got an atom. Okay, so in the center we've got a nucleus. Now in the nucleus you have protons. Let's give this one 2 protons, and it's got neutrons. So let's put 3 neutrons. Then on the outside, it's got energy levels. And in those energy levels, we have electrons. Now, let's say, for example, the electrons are green. So those electrons are negative. Remember that. And then let's say on the outside here, we've got 3. Okay. Now, remember that electrons are negative. Now, let's say, for example, you and I, we would like to walk up to this atom and rob it of its electrons. We'd like to take its electrons away. So we walk up to this atom, we hold our gun to its face, and we're like, yo, bro, give me your electrons now, you know? And so what we do is we always try go for the electrons that are on the outside first, because they are the easiest to remove. But they are going to be a little bit challenging to pull away. Why? The reason is, can you see that in this nucleus, there are some positive protons? There they are. Now, what would those positive protons be doing to these electrons? Well, opposites attract. So there is some type of force that we are going to have to apply, or we're going to need energy to be able to pull this electron away. That amount of energy that we need is called ionization energy. So ionization energy is the energy needed to remove an electron from an atom. And then just remember to say this silly little part at the end. The teachers want you to say it. In the gas phase. Your teacher might use the word gaseous. So it's the amount of energy that you need to remove an electron from an atom which is in the gas phase. Okay, so that's this question. Compare the ionization energy of elements in group number 18. Okay, so I'll have to go get a periodic table now. Group number 18, periods number 1 and number 2. Okay, so let's go grab a periodic table. So here we have our periodic table. Now they said that it must be in group 18. Okay, so that's group 18. Remember the ones going down, those are groups. And then they said period number 1 and 2. So periods is the row. So this is row 1, this is row 1 and this is row 2. So it's in group 18 and it's row 1 and 2. So they want us to compare this one and this one. Okay, so what we need to know is that this is helium, okay? So if I had to draw helium, it definitely has a nucleus, right? And it's got 2 protons, so I'm going to put 2 positives. It has a total mass of 4, so that means it must also have 2 neutrons, because 2 plus 2 is 4. Remember that your protons and your neutrons is what gives you the mass. Now, it's going to be in energy level number 1, right? Because it's in the top row, so it's only going to have 1 ring going around the outside, and it's going to have 2 electrons. Why? Because if it's a normal helium atom, the number of protons and electrons is the same. So that's helium. That is what a atom of helium would look like. Now, if we had to do neon, well, neon also has a nucleus, of course, and it's got 10 protons, okay? So I'm definitely not going to go draw 10 protons, but I'm just going to say 10 pluses, and then it's in row number 2. It's in row number 2. So it's going to have 2 rings going around it, okay? And it's going to have 10 electrons. So your first ring, as I've showed before, always has 2 electrons, and then the rest goes on the outside like this. 3, 4, it's a bit squashed up there, and then 5, 6, 7, 8. So it has a total of 8 on the outside, 2 on the inside, and so it's got 10 electrons in total. Now, I've gone over this in detail before with ionization energy, and the main factor we need to see here is that this distance is a lot less than this distance over here. Because remember, when you and I want to go rob these we want to go steal electrons, we always start on the outside. So because this one has 2 rows or 2 energy levels, it's going to have a much larger distance than this one over here. So which one do you think we should rob? Like, which one would it be really easy to rob? Well, remember that electrons are negative. Okay, so we know that there is an attraction over here, and we know that there is an attraction over here. However, this attraction is going to be much larger than this attraction. Why? Well, it's just because of the distance. If you put 2 magnets close together, it's going to be much stronger than if you put 2 magnets far apart. So which one will be easier for us to remove the electron? Well, it will be this one, because this distance is larger, so that means this force of attraction is weaker, so it'll be easier for us to take this electron away. So that means we need less energy, so the ionization energy will be lower. So we can just say that ionization energy of neon will be lower than helium, because neon radius, remember this is the radius, is larger than helium. That's all we need to say, because it's only for 2 marks. Okay.